Hello, everybody. Welcome back to Math 251. I hope you're having a fantastic day. Today we are learning something new called implicit differentiation, and this is a special kind of derivatives. We know how to take a lot of derivatives now. We have learned polynomials, products, quotients, trig functions, composite functions, e to the x. We know a lot of stuff. So today we are learning another kind of derivative. But first, our mathematician of the day is Caroline Herschel, who was the first woman to receive the Royal Astronomical Society's gold medal in 1828 after she discovered 7 new comets using mathematics. As a child, she had typhus and never grew more than 4 feet 3 inches tall. So she was small but mighty. And did you know that Euclid and Archimedes, who were the inventors of geometry as we know it, started using the symbol theta to denote angles as early as 300 BC? That notation has been around for quite some time. So today we will be learning about what it means to do implicit differentiation. So this far in our course, we have been focusing on functions y in terms of x. We have been finding derivatives y prime, and only when our function is in terms of x. But sometimes we have to deal with functions that are defined in both variables x and y. So, for example, the equation of the unit circle, our good old friend the unit circle, is x squared plus y squared equals 1. If we tried to solve this equation for y, we would get something like y equals the square root of x squared minus 1. And that is only half of the unit circle. So we only end up with the top half, right, instead of the bottom half as well. So this is why we need what we call implicit differentiation. So here are the steps to use implicit differentiation. Implicit means that our function is in terms of x and y. We cannot solve y in terms of x. If we tried to solve y in terms of x, we would get a huge jumbled mess. So we have to use this process when I cannot isolate my x's and my y's on separate sides. So let's go through the step-by-steps real quick on how to use implicit differentiation, and then we will do an example. So our first step is we take the derivative of everything on both sides of the equation. Next, I have to employ the product rule, chain rule, or any other rules in order to find the derivatives. Oops, to find derivatives. Next, I get everything with a y prime on one side and everything without a y prime on the other side. This will make a lot more sense once we do an example. Okay, then I factor out y prime. And finally, I divide to solve for y prime. again, once we do an example, this will make a lot more sense. So let us do this first example. We want to calculate dy dx. Another way that I personally write dy dx as y prime in order to make notation easier, but sometimes you'll see it either way, dy dx or y prime. Directly from the equation of the unit circle and find the slope of the unit circle at the point 1/2 square root of 3 over 2. All right, so we have the equation of the unit circle, x squared plus y squared equals 1. My first step is I need to take the derivative of everything on both sides of the equation. So I take the derivative with respect to x of x squared, the derivative with respect to x of y squared, and the derivative with respect to x of 1. This is step number 1 over here. All right, so the trick here with implicit differentiation is we know that the derivative of x squared is equal to 2x, right? However, the derivative of y squared is not 2y. Again, the derivative with respect to x of y squared is not 2y because we are treating y as a function of x. Y is not a variable here. Y is a function. So in order to find the derivative with respect to x of y squared, we are going to have to use the chain rule. So in order to find the derivative with respect to x of y squared, we have to use the chain rule. So my outer function here that I'm going to call f, my outer function is x squared. My inner function is y. This makes f prime equal to 2x. Here x is my variable, so I can take the derivative just like that. And g prime is equal to y prime. Again, we are treating y as a function, so the derivative of y will always be y prime. It will not be 1 since we are treating y as a function and not a variable. This is very important. All right, so then using the chain rule, I get f prime of g of x times g prime of x is equal to 2y times y prime. So that is the derivative with respect to x of y squared. And I know the other derivatives, so now I have, looking back at this guy, so d dx of x squared is 2x. d dx of y squared I just found to be 2y times y prime. And then d dx of 1 is just 0. So all of this is step number 2 over here. All right, looks like I'm going to have to erase all of this in order to make room here. All right. So my next step is I need to get everything with a y prime on one side and everything without a y prime on the other side. So right now I have 2x plus 2y y prime equals 0. Here I only have one term with a y prime, so I'm going to move that one over to the other side. 2y y prime minus 2y y prime, and I get 2x equals minus 2y y prime. This was step number 3. Finally, I factor out a y prime. So when I factor out y prime from this side, I am left with negative 2y. This is step number 4. And my last step is I divide out to solve for y prime. So I get y prime equals 2x divided by negative 2y, or simply negative x over y. So this is y prime. This is what I want. This represents the slope of the unit circle at any point x and y. here I do have a point that I want to find the derivative at. I want to find the derivative at 1/2 square root of 3 over 2. So if I plug in the point 1/2 square root of 3 over 2, I get y prime equals negative x, whoops, that is negative 1/2 over square root of 3 over 2, which is equal to negative 1 over square root of 3. This means that the slope of the unit circle at the point 1/2 square root of 3 over 2 is equal to negative 1 over the square root of 3. That represents the slope on the unit circle at this point. Whew, that's a lot, isn't it? All right, let's do another example. We want to find y prime when we have the function sine of xy is equal to x squared plus y. Now, this xy here, we're taking the sine of this whole thing. So I cannot solve for y strictly in terms of x. My y's and my x's are all jumbled together. I cannot solve for y in terms of x. This means that I have to use implicit differentiation. So I have to use implicit differentiation. My first step is I take the derivative with respect to x of everything on both sides of the equation. Step 1. Now to find the derivative of sine of xy, I'm going to have to use the chain rule since I have a function xy inside another function sine. So here I'm going to have to use the chain rule to find the derivative. So my outer function is sine of x. I'm just going to say f. So f is equal to sine of x, and g is equal to xy. All right, well, I know that the derivative of sine of x is equal to cosine x, but we have to be careful when I'm taking the derivative of g here, because now I have to use the product rule, since I'm multiplying two functions together. So g prime, I have to use the product rule, which says that I take the first times the derivative of the second. The derivative of y is y prime, plus the second times the derivative of the first. We are treating x as a variable, so the derivative of x is equal to 1. And then from here, I can use the chain rule. So the chain rule says that I have f prime of g of x times g prime of x. In this case, we have f prime of g of x is cosine of xy times xy prime plus y. This is the derivative of sine xy. So then going back up here, I have that the derivative of the left-hand side is cosine of xy times xy prime plus y is equal to, and then I have to take the derivative of x squared, which is 2x, and the derivative of y, which is y prime. All right, so this is my derivative here, and this was step number 2, finding the derivative. My next step is that I want to get everything with a y prime over on one side of the equation and everything without a y prime on the other side. So in order to do that, I first need to distribute or expand this first side in order to do the y prime stuff. So if I multiply cosine xy times xy prime, I get xy prime times cosine of xy plus y cosine xy. So I just distributed my cosine of xy to xy prime plus y is equal to 2x plus y prime. All right, and now I am in a good position to move everything with a y prime over to one side and everything without a y prime over to the other side. So in order to do that, I'm going to move this y prime over to this side to make the left side the side with the y primes, and I'm going to move this term without a y prime over to the other side. So when I do that, I will get the following: x y prime cosine xy minus y prime is equal to 2x minus y cosine of xy. This was step number 3, getting everything with a y prime over to one side and everything without a y prime over to the other side. Now I need to factor out a y prime from the side with the y primes. When I do that, I get y prime times x cosine xy minus 1 equals 2x minus y times cosine xy. This is step number 4. And finally, in order to solve for y prime, I need to divide everything by what y prime is currently being multiplied. So I'm going to divide both sides by x cosine xy minus 1. And I get y prime equals 2x minus y cosine xy divided by x times cosine xy minus 1. Whew, this is pretty fun, huh? I think so. This is our last step right here. Dividing out that y prime in order to solve, dividing out what y prime was being multiplied by in order to solve for y prime. So again, here we knew that we had to use implicit differentiation since I could not solve this function for y in terms of x. I had to use the chain rule in order to find the derivative of sine of xy. And then I had to use the product rule to find the derivative of xy. And then I just followed my steps. I had to expand out a little bit. I got all of my y prime terms to one side, all of my terms without a y prime on the other side. I factored out a y prime where I could, and then I divided through to solve for y prime. I know these examples are pretty long and involved, so I think if you're lost, it might be beneficial for you to go back and watch this example again. That way you can kind of get a feel for the flow of these kinds of examples. All right. I would like for you to pause this, and if you're feeling very brave, go ahead and try example number 3 on your own. I believe in you. I think you can do it. So go ahead and give it a try, and then we'll come back together and do it together. All right. So actually this question, sorry, there's a typo here. This should just say find the slope of the tangent line. Sorry about that. All right, so again, we cannot solve this equation for y in terms of x, so I have to use implicit differentiation. My first step is to take the derivative of everything on both sides. Very important to do both sides, otherwise you'll end up with a constant where you don't actually have one. All right, this is my first step. And now I need to take some derivatives. I know the derivative of x squared. That one's easy. In order to find the derivative of 2xy, I am going to have to use the product rule. So let's look at this one first. So if I find the derivative of 2xy, I'm going to have to use the product rule. So I'm going to set f equal to 2x. You could put the 2 wherever you want, really. And I'm going to set g equal to y. This makes f prime 2 and g prime y prime. So this gives me the first times the derivative of the second plus the second times the derivative of the first. So 2xy prime plus 2y is the derivative of 2xy. In order to find the derivative of y cubed, I have to use the chain rule, since I have a function, y, and times another function, something cubed. So here, I'm going to have to use the chain rule. So the chain rule says that my f of x is my outer function. In this case, it's x cubed. My inner function here is y, which means that f prime is equal to 3x squared and g prime is equal to y prime. So now I take f prime of g, that's 3y squared, times g prime, which is y prime. All right, so now I have my derivatives of everything, and I can plug back into my equation up here. Do you guys hear my dog in the background? I'm sorry. All right, so the derivative of x squared is simply 2x. I found the derivative of 2xy to be 2xy prime plus 2y, and the derivative of y cubed is 3y squared y prime equals the derivative of 9, which is 0. All of this was step number 2. All right, now I need everything with a y prime on one side and everything without a y prime on the other side. I'm going to subtract everything without a y prime to the other side. So I'm going to subtract this 2x and this 2y. And that gives me 2xy prime minus 3y squared y prime equals negative 2x minus 2y. All right, that was step number 3. Getting everything with a y prime to one side, everything without a y prime to the other side. And now I'm going to factor out a y prime from everything that I can. So when I factor out a y prime on this left side, I get 2x minus 3y squared equals negative 2x minus 2y. This is step number 4. And finally, I divide through in order to solve for y prime. So I divide by 2x minus 3y squared. And I get y prime equals negative 2x minus 2y over 2x minus 3y squared. Woo! What a booger. So this is the slope of this curve, x squared plus 2xy minus y cubed equals 9. and I want to find the slope at the point 3, 0. So actually what I want to do is I want to pull up Desmos real quick to show you what this curve looks like. Just so you can see that it's not a function how we usually think about functions. So I have x squared plus 2xy minus y cubed equals 9. So this is what our function looks like. And we can see pretty easily that it does not pass the vertical line test, which means that it's not a function as we know it, since it is in terms of x and y. And I want to find the slope of the tangent line at the point 3, 0, which is right there. So I'm trying to find the slope at this point right here. I've just solved for y prime, so that is the slope for any point on this function. So now I'm going to plug in the point 3, 0. So at 3, 0, I get y prime equals negative 2x. That gives me negative 2 times 3 minus 2 times y, which is 0, over 2x, which is 3, minus 3, 0 squared, which gives me negative 1. So the slope of the tangent line on this super funky curve at the point 3, 0 is negative 1. All right. I have included a lot of examples in this section because I know this can be a bit challenging at first, so that's why we have so many examples that are pretty long and involved, just to give you some more practice and some more exposure to different kinds of problems. All right, in example 4, we want to find the slope of the curve of 2 times x plus y to the power of 1/3 equals y at the point 4, 4. So let's graph this equation to see what it looks like. I think these kinds of equations can be fun to see. So we have the function 2 times x plus y to the power of 1/3, whoops, equals y. Yeah, so pretty strange. We have the point 4, 4 here that we are concerned about. If I can show you. Oh, here's the point 4, 4. And so that's where we want to find the slope of the tangent line. Again, this function does not pass the vertical line test. It's not a function as we normally think about it. It is called an implicit function. All right, so we are going to have to use implicit differentiation here, of course. So I first take the derivative of everything on the left and the right side. So I have the derivative of 2 times x plus y to the power of 1/3 equals the derivative of y. And actually, first, just for simplicity's sake, I'm going to bring this 2 out in front. That's the constant multiple rule. So I can take 2 times the derivative of x plus y to the power of 1/3 equals the derivative of y. That's step 1, taking the derivative with respect to x of both sides. So in order to take the derivative of x plus y to the power of 1/3, I'm going to have to use the chain rule here because I have a function, x plus y, inside of another function, something to the power of 1/3. So here I'm going to have to use the chain rule. So my outer function, f, is x to the power of 1/3. My inner function is x plus y. This makes f prime, using the power rule, 1/3 x to the power of negative 2/3, and g prime equals the derivative of x is equal to 1, and the derivative of y is y prime. So using the chain rule, I get f prime of g of x times g prime of x equals 1/3 times x plus y to the negative 2/3, that's f prime of g of x times g prime, which is 1 plus y prime. So this is the derivative of x plus y to the power of 1/3. We can't forget about that 2 out in front. So this was all step 2, finding the derivative. So plugging this back into our original equation, I get, again, I have that 2 out in front. So my derivative here on the left-hand side is 2/3 x plus y to the negative 2/3 times 1 plus y prime. And then on the right, I have the derivative of y is just equal to y prime. Now I'm going to have to multiply out the left-hand side in order to see which term has a y prime on it and which term does not. So I'm going to multiply this out, multiply all of this by 1 and then by y prime. So when I do that, when I multiply it by 1, it's just itself. So I get 2/3 x plus y to the power of negative 2/3 plus y prime times 2/3 x plus y to the negative 2/3 is equal to y prime. I simply multiplied out the first 2 terms in order to see which term has a y prime on it and which one doesn't. I can see that one of my terms does have a y prime on it. So I'm going to subtract this term over to the other side to get everything with a y prime on it on one side and everything without it on the other. So I subtract y prime times 2/3 x plus y to the negative 2/3. I subtract this from both sides. That is step 3. This leaves me with 2/3 times x plus y to the negative 2/3 equals y prime minus y prime times 2/3 x plus y to the negative 2/3. Next, I need to factor out a y prime from the right-hand side. When I do that, I get 2/3 x plus y to the negative 2/3 equals, factoring out a y prime gives me 1 minus 2/3 x plus y to the negative 2/3. That is step 4. And finally, I divide through in order to solve for y prime. So I divide both sides by this guy over here, and I get y prime equals 2/3 x plus y to the negative 2/3 over 1 minus 2/3 x plus y to the power of negative 2/3. Now you may be tempted here, since I have a 2/3 x plus y to the negative 2/3 on the top and the bottom, you may be tempted to cancel those two out. However, since we are subtracting instead of multiplying on the denominator, we cannot cancel those two things out. This is as simplified as it can get. And we want to find the slope of the curve at the point 4, 4. So now I'm going to plug in x equals 4 and y equals 4. So at 4, 4, I get y prime equals 2/3 times x plus y is 8 to the power of negative 2/3 over 1 minus 2/3, 8 to the power of negative 2/3. And if you'd like, you can plug this into your calculator, but you would get 1/5. 1/5. So the slope of our tangent line at the point 4,4 is 1/5. And if we were to look at the graph at the point 4,4, that looks about right. It's a pretty shallow positive slope, so 1/5 makes sense. All right, we have one more example. We want to find the second derivative of the unit circle equation. So we have already found the first derivative of the unit circle equation in example number 1. So in example number 1, we found the first derivative was y prime equals negative x over y. We already found this in example number 1. Now I want to find y double prime. So in order to find y double prime, I have to take the derivative of both sides, right? So my first step, as always, is to take the derivative with respect to x of y prime, the derivative with respect to x of negative x over y, step 1. The derivative of y prime is just y double prime. Actually, we'll save that for later. But here, negative x over y, I'm going to have to use the quotient rule, since I have a function over a function. So my top is equal to f, or negative x. My g is the bottom, that is y. So I have f prime equals negative 1, and g prime equals, be careful here, y prime. So then the derivative of negative x over y is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom. All of this over the bottom squared. So this was step 2, finding the derivative of both sides. So I have on the right side, I have y double prime here in this equation. I have y double prime equals, and then I just found the derivative of negative xy, negative x over y. That was negative y plus xy prime over y squared. So I want to find, again, the second derivative, y double prime, but I want it only in terms of x and y. So the second derivative, if we think about this like maybe in terms of position, the second derivative is acceleration, and the acceleration might depend on only the position x and y, not on y prime. So I want to get rid of the y prime that I have in here and solve for y double prime only in terms of x and y. So if I replace this y prime with what I already know y prime is, I already know y prime is equal to negative x over y, I get the following. Y double prime is equal to negative y plus x times y prime, which is negative x over y squared. And from here, I can simplify this a little bit. So I get negative y minus x squared over y squared. I want a common denominator here in my numerator. So my common denominator will be y, which means that I need to multiply this term right here times y over y. That gives me negative y squared over y minus x squared over y squared. Now I have a common denominator in my numerator. I have negative y squared minus x squared over y, all of this over y squared. So now I have a fraction in a fraction, and I can multiply the top by the reciprocal of the denominator. So this equals negative y squared minus x squared over y times y squared, which is y cubed. And we are almost done. You could leave it like this, but there is one more trick up our sleeves. Remember, this is the unit circle. The unit circle says x squared plus y squared equals 1, right? So if I factor out a negative on the top, I get y squared plus x squared. And the unit circle says x squared plus y squared equals 1. So this is really negative 1 over y cubed. So, interestingly enough, the second derivative of the unit circle equation only depends on our y value. That is pretty interesting, I think. So, yeah, this is the second derivative of the unit circle equation. We had to replace our y prime with what we already knew our y prime was. That was our first trick. And then the second trick was recognizing that I have y squared plus x squared in there, which according to the unit circle is equal to 1. Wow, this was a lot today, but I wanted to give you guys a lot of examples to see and work through. Again, feel free to go back and rewatch some examples that I just did if you are feeling iffy on it. I'm happy to answer questions during our Zoom meetings. So other than that, I will hopefully see you at our Zoom meetings and hope you have a great weekend.